You're watching a Channel 98 NBISD TV production.
Hey, welcome to That Geometry Show. I'm Kevin Corpy, back from the 70s, and I'm going to be your host again today. Imagine that, for lesson number 9. Today we're going to be talking all about triangles again, more triangles. A little bit different about triangles. We're going to be talking about combinations of angles, combinations of sides. It's going to be a lot of fun. So why don't you go ahead and log on to the internet, download those sheets. Those sheets, by the way, they're free, okay? www.newbraunfels.txed.net. So please download them. I spent a lot of time making them, and it's nice to have them in front of you. I'll wait for you to download them. We don't have the time, actually. So DVR this, play it back if you want. Play it back as many times as you want. There's no rule that you can't watch it more than once. Let's go ahead and get started. All right, lesson 9. This is going to correspond with your Glencoe Geometry textbook, chapters 4.3, 4.4, and 4.5. We're doing 3 sections today, a lot of information. We're going to explore congruent triangles. Okay, so by the end of the show, you should be able to, number 1, name and label corresponding parts of congruent triangles. Number 2, you should understand the 3 types of congruence transformations. And number 3, you should be able to determine if 2 triangles are actually congruent. All right. Now, as you know, this week we are sticking with our topic from last week, triangles. And they are by far, really, the most popular geometric figure in the whole wide world. So, go figure. Because they're the most popular, there's a lot of examples. We're going to have to spend a lot of time talking about them to make sure you have all the information down. Okay, now, when we're working with multiple triangles, more than one triangle, it's very, very important to recognize if any of the triangles are the same size and the same shape. Size and shape are 2 important aspects of triangles when you're dealing with more than one of them. Okay? If you have 2 triangles that are the exact same size and the exact same shape, then we can say that the triangles are congruent to each other. And we've talked about congruence a lot this year. Congruent just means equal measure. Okay? Well, what are we measuring in a triangle? Remember that triangles have 3 parts. 3 parts on the inside, 3 parts on the outside, actually, for a total of 6. So they have 3 angles in this triangle, triangle A, B, C. We have 3 angles on the inside, angle A, angle B, and angle C. And they have corresponding sides. We have side AC, side CB, and side BA. Now, I'm just putting marks on here to show you what the sides are. These marks, later on in the program, are going to take on a new meaning. Okay? But anyway, 1, 2, 3 sides, 1, 2, 3 angles. All right. Now, a triangle that is created by means of the same triangle by means of what we're going to call a transformation. And the transformation, in this case, is going to be called an isometry. Now, an isometry is a special type of transformation. It's going to be a congruence transformation, which means when we change the graph, it's not going to change the shape and it's not going to change the size. There are some transformations that will change the shape and or the size, and it's not an isometry. Another name for these types of transformations are called rigid transformations, and the word rigid implies that the size and shape are staying the same. All right, so there's 3 types of rigid transformations, 3 types of congruence transformations, or 3 types of isometries. They all mean the same thing. The first type is a reflection across a given line. So let's say that we were starting right here with this triangle, triangle IJL. And this is a given line. It can be anything that doesn't intersect through the triangle. Well, you could think of this line as being a mirror. And so I could take this triangle and basically reflect it, boom, like that, across the line. So that point L, its mirror image is going to be L prime. Point I has a mirror image of I prime. And point J has a mirror of an image of J prime. The distance from J to our line and from the line to J prime is going to be the same distance. So basically, when we reflect across the line, we preserve the shape, we preserve the size. What we do is we basically invert it. But anytime we have a reflection across any line, we can say that the two triangles are congruent. So we could say that triangle IJL is congruent to triangle I prime J prime L prime. So remember how we name triangles. We name them with the three vertices of the three angles. Now notice also in here that I'm calling the original triangle IJL, I, J, and L, and it's congruent to I prime, J prime, L prime. So the order of the letters in naming the triangles is very important for congruent triangles because they're going to be corresponding letters. And the prime just means that it's related to I or related to J, but it's in a different location. Okay, so reflection across a line is a rigid transformation, and any graph of a triangle that's generated across a reflection of a line is going to be congruent. Good. Now the next type of rigid transformation or isometry is a rotation about a given point. So let's look at this triangle down here. Triangle GFH. Triangle GFH. You can pick any point that's not in or on the triangle. I've chosen point I right here. Now, if I hold it down at point I with my pencil, I can rotate this thing around. Now, the relative positions of this red triangle on your TV screen is going to create an isometry. Okay? And as we rotate it around, we can draw as many of them as we want. What I've shown here is I've shown 1, 2, 3 other possible triangles that we get by rotating it around. And all of these triangles are congruent to each other and to the original triangle. So we could say that triangle GFH is congruent to, and now we want to make sure that we name the congruent triangles in the same order. The first one would be G prime, F prime, H prime, G prime, F prime, H prime, which happens to also, oops, I forgot my triangle symbol. We need that, -1 for Mr. Corpy. Congruent to triangle, well, the next one in the same order would be G double prime, F double prime, H double prime. So the same order, G double prime, F double prime, H double prime. And finally, that one is also congruent to the final blue one, which is going to be some GFH, but it's up here and we're calling it triple prime. So G triple prime, F triple prime, and H triple prime. They are all congruent to each other because they are rotations of the original triangle, which is a rigid transformation or an isometry. Okay, so that's 2 of the 3. The third one has 3 different names. All right? In math, sometimes we have several names for the same thing, like isometry, rigid transformation, and congruence transformation. The third type of isometry can be called a shift, it can be called a slide, or a translation. And basically what that means, those are fancy names for just picking the graph up and moving it somewhere and setting it right back down. We're not rotating it, so it's maintaining the same orientation. We're not flipping it, we're just moving it. Okay? So if I start with triangle ABC, and I moved point B over here, and I moved point A over here, and I moved point C over there, I generate a congruent triangle. So I could say triangle ABC is congruent to triangle A prime, B prime, C prime. It's just in a different location. It is shifted, it has slid over, or it has been translated over. And it doesn't have to be just directly to the right or to the left. We can move it to the right and at an angle, or left and at an angle, or down and at an angle. So this original triangle here, triangle DEF, if I translate it or slide it, I can move it over here, and these points correspond to each other. So in this case, triangle DEF would be congruent to triangle D prime, E prime, F prime. Okay? Now let's look at one quick example here of a type of isometry that may or may not be. Okay, here's an example. Is this transformation going from triangle ABC to this triangle GHI, is it isometry? Is it a rigid transformation? Well, that's going to depend on whether or not these two triangles are congruent. Just looking at it on your TV screen there, do they appear to be the same shape? Well, they actually do. They are both triangular, and they appear to have the same shape, but are they the same size? It appears that this triangle on the right is actually a little bit smaller than this triangle here. So it's more than just a shift or a slide or a translation. A is not just going straight across to G. A is actually going down to G, C is going straight across to I, and B is going up to H. So this is not an isometry, because it not only moves the position, but it changes the size. This is actually not a rigid transformation either. This is called a dilation. A dilation is kind of like when you get your eyes dilated. It stretches by the same factor. Okay, so a dilation is kind of a stretching or shrinking of the triangle, and it changes the size. And a dilation is not an isometry. It's a different type of transformation, but we're not going to be looking at those for congruent triangles. This actually deals with another important concept called similarity, and we'll talk about that later on. But these are actually similar triangles, but they're not congruent. Today we're talking about congruence. Okay, so that's what happens if we have two triangles that are generated from some type of rigid transformation or an isometry. But what if we're starting with two separate triangles that are not created from an isometry? How could we then determine if the two given triangles are congruent? Well, here's a real easy way to tell. Remember, we had 6 parts of a triangle, 3 on the inside for the angles, and then 3 around the perimeter of the 3 sides. If all 6 of the corresponding parts of any two triangles are congruent, which means equal measures, all the angles are the corresponding angles are the same size, corresponding sides are the same size, then we can say they're congruent. Okay? Now this is actually an if and only if statement, so it goes both ways. If we know they're congruent, then all the corresponding sides are congruent, and if all the corresponding sides are congruent, then the triangles are congruent. Now, remember those tick marks I drew at the beginning of the show when I was just labeling the 3 sides? They actually have specific meaning. Look at these two triangles here, triangle ABC and triangle DEF. Okay, if we knew that segment AB was congruent to segment DE, those are corresponding parts on 2 different triangles because they're in the same position. If we knew they were congruent, we could put a tick mark on there. And that single tick mark shows that both those are the same size. Working away around the 3 sides, if we also knew that side BC or segment BC was congruent to the corresponding side, EF, we would have to put a different mark. So since we've already used the first mark, we'd have to use a different mark. And in this case, we've chosen 3. Okay? The 3 marks on each means they're congruent to each other, but they're not congruent to these others right here. All right, now down here we have segment AC is congruent to segment DF, and we know that because they both have the double tick marks. Now if in fact all 3 of these sides are congruent to the other, but none of them are congruent to each other, that means each of these triangles have side lengths that are all 3 different lengths, which means, remember from last week, these would be scalene triangles. Okay, well, certainly then if we knew also that the angles, and instead of tick marks we draw little angled marks here, so if we knew angle A was congruent to angle D, and angle B was congruent to angle E, this time using double tick marks, and angle F was congruent to angle C, again using triple angle marks, then we would know that all 6 parts, corresponding parts of these 2 triangles were congruent, so they have to be really congruent triangles. So then we could say that triangle ABC is congruent to triangle DEF. Wow. Let's go ahead and take a short break to watch some public service announcements, but don't go anywhere. We're going to be right back.
I smoked weed and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot at dying out there in the real world. Jiving hard to the rim, ice skating with a girl. Now you want to keep yourself alive, you go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
Twinkle, twinkle, little star, how I wanna know what you are. Up above the world so high, like a diamond in the sky. Twinkle, twinkle.
The odds of a child being in a Broadway show are 1 in 11,000. The odds of a child being diagnosed with autism, 1 in 166. The odds say it's time to listen. To learn the signs of autism, visit autismspeaks.org.
Hey, welcome back to That Geometry Show. I'm Kevin Corpy still Kevin Corpy, and today we are still doing lesson number 9 about congruent triangles. And you know, during that break I've kind of missing the math, so why don't we get right back to it. Okay, so let's summarize what we know then about the 6 parts of 2 congruent triangles. We have 6 pieces of information, or 6 facts, okay? So we could say in these two triangles, triangle ABC and triangle DEF, if we know their triangles are congruent, then we know that segment AB is congruent to segment DE, its corresponding part. We know that segment BC is congruent to segment EF, its corresponding part. And segment AC would be congruent to segment DF, its corresponding part or corresponding side. So that takes care of the side lengths. We also know then that angle A would be congruent to its corresponding angle, angle D. Angle B would be congruent to its corresponding angle, E. And finally, angle C would be congruent to its corresponding angle, angle F. All right? 6 pieces of information, 6 facts about congruent triangles. So all we have to do to show that two triangles are congruent is show all 6 of those things. That's a lot of work. Now again, very important. Here's what this guy says. VIP, very important. Okay? So here's what he's saying, which I've already mentioned. The order of the letters in the names of the triangles. So we'd say triangle ABC then is congruent to triangle D, triangle DEF. The lettering of the names of the triangle is very important because it displays the corresponding relationships. So up here in triangle ABC is congruent to DEF, we know that angle A, which is the first letter, would be congruent to angle D, the first letter in the other name. We also know that segment BC, that would be the last 2 letters in the first triangle, would be congruent to segment EF, the last 2 letters in the second name, because they are in the same position in each of the names of the triangles. So you have to be very careful. You could not say that triangle ABC above is congruent to triangle EFD, because that's not the order of the corresponding parts. So be very careful and very deliberate when you know you have 2 congruent triangles that you're naming them in the same fashion, in the same order. Okay? Luckily for us, if we are trying to prove that 2 triangles are congruent, we don't have to actually show all 6 things. There are certain combinations of the 3 sides and the 3 angles that are sufficient, that are enough to prove that 2 triangles are congruent. The first case that we're going to be looking at is the SSS case, or the side-side-side case. And here's what the side-side-side case says. It says, if 3 sides of any triangle are congruent to 3 sides of another triangle, in this case we could say that this side here would be congruent to this side, if we knew that, and we knew that this side here was congruent to its corresponding side, and if this bottom side here, I'll do 3 marks, 3 tick marks, is congruent to the corresponding side over here, we don't need to know any information about the angles. We could automatically conclude that these 2 triangles, notice I haven't named them, but they are 2 separate triangles, that they are in fact congruent. Which means knowing 3 sides are congruent, it means the 3 angles are also congruent. Because congruent triangles means all 6 parts are congruent, the corresponding parts. So side, side, side. If you have 3 sides, don't know any angles, but you know they're congruent, you know the triangles are congruent. All right. The next combination is knowing 3 pieces, a side, an angle, and that in angles is important. It's between the SAS, it's side, angle side, that means it's the included angle. So here we go. If 2 sides and the included angle of one triangle are congruent to the corresponding parts of another triangle, the triangles are congruent. So here's what I mean by side, angle, side. Let's say I knew this side was congruent to this side. Oops, I'll better put 2 there. And what if I knew that this side was congruent to that side? So I have side congruent to side congruent to side. The included angle would be the one that's formed by the 2 sides. So I'd have to know that this angle would be congruent to that angle. Now I have side, angle, side. And if I know the corresponding parts, side, angle, side, are congruent to each other, then I know the triangles are congruent, which means all the other parts that we don't know have to be the same measure. Now there really is no reason why it has to be this side, the top angle, and the other side. If I would have started with this side here, and let's say this side, knowing that this side and this side were congruent, well then I would need to know something about these angles. I would need to know that these angles were congruent, because those would be the included angles for these 2 given sides. So any 2 sides with their included angle in corresponding triangles is enough to prove that 2 triangles are congruent. Okay, so we got side, 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 and side angle side. The next case is the ASA case, which stands for angle side angle. And again, that side needs to be the included side. So here's it is stated. If two angles and the included side of one triangle are congruent to the corresponding parts of the other triangle, the triangles are in fact congruent. So let's label it. Let's say I know this angle, I know this side, and I know this angle are congruent in this triangle, the corresponding parts, this angle, this side, and this angle. That would be enough to show that all the other parts which are not labeled are also congruent, which would make the triangles congruent to each other. And again, it doesn't necessarily have to be any two specific angles. I could have started with this angle here, and let's say I had this angle and this angle. What's important is that we know this angle, and then the included side. So that in this case would be here. So if I knew side angle side, it would also work. It shows that they're congruent. All right, moving right along here. There are two more, so we're getting close. This next case is the angle side, which is equivalent to side angle. One we're just reading from left to right, and if we read it from right to left, we get side angle. Okay? So here's what it says. If two angles and the non-included side, notice the S is outside the two A's, of one triangle are congruent or to the corresponding parts of the other, then the two triangles are congruent. So here we go. Let's say we have this angle. Let's say we have this angle and the non-included side. So let's say we didn't know that one. We could have either this one here, that would be angle side, or we could have this side, that would be angle side. It doesn't really matter. Let's say I had this one on the bottom. So now I would need to know in this other triangle that this angle is congruent to that one, corresponding parts. This angle is congruent to that one, and I would need to know the same side, whether it was the top one or the bottom one. So now by the side angle or the angle side, since the corresponding parts are congruent, I could then conclude that the triangles are in fact congruent, which means again that the other side, the other two sides and the other angle are also congruent, the corresponding angles and sides. So congruent triangles. All right, now the next case is very important to understand that it is a special case. In the case of a right triangle, the previous ones worked for any triangles. But if the hypotenuse, remember which is the longest side opposite the right angle, and one of the legs, one of the two shorter sides in a right triangle are congruent, then the triangles are congruent if the corresponding parts are the same. So remember in a right triangle, that means that we have a right angle. And we usually denote that with this little box here. So if we know that the hypotenuse of one is congruent to the hypotenuse in the other, and the leg, let's say I had this leg here, that leg was congruent to this leg. Now I can say in a right triangle only that they're congruent. Now look to see what we have here. We actually have a side, and the non-included angle. That would be SSA. Or we can read it the other way, the angle side. So that's equivalent to saying the angle side. We haven't looked at that case above. And you're going to see in a second here that this combination, side angle or angle side, is not always going to give you congruence of two triangles. But in the special case of a right triangle, we can say that it will. Which brings us nicely, a nice segue into the part of the section we call the Say What section. Here's what we're doing today. We're looking at two other cases that will not work. Okay? So let's look at other conditions other than the combinations that we looked at. And the first one that we are going to visit is the side angle or the angle side. So here we go. The side angle and the angle side does not work. Now here's an easy way to remember it. I'm not going to say this word, but looking at it on the TV screen, you know that this is a word that you should not say. Bad word. Doesn't work. Okay? Don't say the word. Don't use this method to assume two triangles are congruent. Okay? Side angle, angle side. Caution, roadblock, stop. Here's why it doesn't work. Look at this little diagram here. In this diagram, I can look at having an angle and two sides. So let's say I have this angle here, angle A, and then this side, angle B, and another side, call it A1. Okay? I know that this angle has to be fixed, so this angle right here with the bottom can't move, which means that this arm is pretty much fixed. But since this angle up here is not specified, I can think of this point up here as being a pivot point. And I can let this leg right here, I can kind of let it swing back and forth freely like a pendulum, okay? And wherever it intersects with the base of this triangle, I can get a possible triangle. So angle side side would give me this triangle here, this obtuse triangle, but just by making this angle bigger, which we weren't given any information about it, I can swing it across, and when it intersects with this point over here, I get this larger triangle out here, which I'm going to draw on the outside. So I get two possible combinations, okay? So whenever you get to the angle side side case, you're going to want to stop. Okay, be careful. We get two possible combinations. We don't know necessarily if they're congruent. They still might be, but we need some more information. We would need to know another angle or another side so that we can pin it down. All right, the other case, and I know you're all wondering about this, would be the angle, angle, angle. What if we didn't have any information about the sides, but we knew that in two triangles, all three angles were congruent? Would that constitute congruent triangles? Well, we need at least one side length, and I'll show you why. So it's not going to work. Okay? We can, however, conclude that if all three angles are the same, that the triangles are going to be similar. Okay? Now, similar means proportional, and that's going to come up on a later lesson. That's where corresponding parts are factors of each other, or multiples of each other. The two triangles are dilations of each other. Now, angle, 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 they still could be congruent, but in general, they're not. And here's a good example. Y'all been looking at this logo a lot. The logo for that geometry show is a very good example to show that if we just have three angles, the two triangles are not necessarily congruent. Let's look at this smallest triangle that's in this awesome logo right here. Okay? In this triangle right here, I can say that I have this angle. I know it's kind of hard to see, and I have that angle there. Well, look at this other triangle that's outside of it right here. This other triangle. It's a little bit bigger. These two triangles that I've outlined are actually proportional. They are similar to each other because this angle here of this bigger triangle is going to be congruent to this triangle of the smaller one, and this angle here is going to be congruent to this angle, and this angle here is going to be congruent to that one. So there we go. All three angles, in fact, are congruent, but notice that the yellow triangle is smaller. It has a different size. The shape is the same, but the size is different. So these would be dilations of each other. And we've already talked about dilations not being rigid transformations. They are not isometries. Okay? So two triangles with all angles the same are not necessarily congruent. We would need at least one side length to make a determination whether or not they are. All right, that was a lot of information today. Not a lot of examples, but a lot of critical information that you're going to need to be able to do geometric proofs in class. So please memorize that stuff. Work these worksheets more than once, twice, 3 times. Your teachers will love you. The harder you work, the better you're going to get. Until next time, I'm Kevin Corpy, and I will catch you on the flip side.
You're watching a Channel 98 NBISD TV production.